2023年明けましておめでとうございます。以前に投稿した人間は何度も生死を繰り返すについて、なぜそのような発想を思いついたのか、その根拠は何かを簡単に説明します。以前に投稿した人間は何度も生死を繰り返すについて、なぜそのような発想を思いついたのか、その根拠は何かを簡単に説明します。これは2022年12月22日に投稿した前回投稿の最後半部分の文章。さらに生命の有限性によっていつかは支配階級一族が死滅すれば新しい一族は新しい意識を持つのかと問われるかもしれない。さらに親の遺伝傾向は物質構造として引き継がれるのなら、支配階級一族の意識は何も変わらないと言われるかもしれない。しかし、量子力学によって生命現象が営まれるなら、新生回帰は必ず発現するはずであり、人間や生物一般はそれを信じるのみであるの部分です。つまり、遺伝情報は体内の物質組成にできるだけ誤りが起きないように正確に組み込まれ、これにより両親の身体特徴に類似した子供が誕生します。さらに、それは身体特徴だけではなく、性格や行動特性全般にまで影響を与えます。これは遺伝子疾患を防ぐためにもかなり正確なものだろうと考えられます。意識が物質の構造組成から発現するとした場合、子供が持つ意識は、そのような親の意識特性を受け継いでいるとも考えられます。さらに、現在の科学では、意識の発現が科学では説明できない以上、これを否定できません。そうであれば、遺伝によって、経済階級や生活環境などが、おのずと類似するとも考えられます。インドで起きた生まれ変わりを主張する少年の事件ですが、ある時その少年は知らない住宅に行き、かつて自分はここで暮らしていたことがあると主張しました。しかも知らないはずの生活様式の一部を言い当てたと伝えられています。このように、その知らない住宅が同じような経済階級や生活環境である場合、この少年の主張を完全には否定できません。ただ、脳の構造組成や形状特徴によって意識が発現するという説では、今回の世界大戦によって多くの戦死者とともに多くの頭部損傷の傷病者を出しました。その追跡調査で、頭部損傷の傷病者の多くは、頭部実質の破損や頭部神経系の断裂によって、それによる視野狭窄などの身体活動の不具合を訴えましたが、頭部実質の破損によって意識に変調が起きたとか、意識すら世界が明らかに変わったという訴えは、頻度としては少なかったようです。これは、重度の精神疾患に頭部実質の広範囲の物質的変化や局所的な大きな脱落が見られないことも意味します。また、現在も重大な交通事故は発生して脳損傷もそれに伴い起きていますが、それによる精神疾患の発症頻度が少ないからといって脳実質が意識を発現する要因であることを完全に否定できる根拠にはなりません。それでは、現時点で脳実質が意識を発現する要因として、最も大きなものを挙げるとしたら何があるでしょうか。それは、1925年頃に整備され、非局所性や遠隔相関や観測による物質運動の一斉変化を持つとされる量子力学も一つの候補だと投稿者は考えます。この宇宙誕生による物質の大変動を経て、地球での生命誕生は約35億年前に海で発生して、その栄意が続いているとされています。生命誕生では、 自他の区別を持つ活動個体が進化し発展していきますが、その活動個体の活動源は量子力学の非局所性であり、宇宙全体の活動に帰するのではないかと投稿者は考えています。投稿者が、個々の生命体が自他を区別する自発性や自意識を持つのは、生命性は自他の区別がない正規論や半身論のような大きな層であり、そこで生死する生物個体は量子力学によって活動するのだと考えます。そこで、自他を区別する自発性や自意識を獲得する基準は未だ不明ですが、量子力学として確認される物理現象である、非局所性や遠隔相関や観測による物質運動の一斉変化も、未だ、現在の科学では説明不能であり、そのため、現在の生命活動は、量子力学が関係する一つの候補だと投稿者は考えます。特に、生命保有期間は人間では約80年から90年であり、意識は遺伝による脳の物質的形態により発現するのではないとするなら、この生命の有限性は別の理由からと考える必要があります。それは、物質運動は次々に伝播していく決定論的運動とされていますが、それを完全に消去するようなランダムなシステムが自然には必要なのかもしれません。そのため、自然に生起した生物個体、特に人間の記憶は完全に消去されるのではないかと思われます。次の映像は、意識の成立に関するロジャー・ペンローズ教の公開講演会の映像です。この映像はクリエイティブコモンズが宣言されているので、投稿者も使用させていただきました。放映時間は1時間20分32秒です。
Operations in microtubules inside brain neurons corroborates this theory according to review authors. So it has taken off again, and I think that just as easily brings us to where we are at this point. Roger has been doing so many other things in physics and mathematics and art, Penrose tiles and Penrose diagrams and so on and so forth. So let me just introduce him and we'll take it from there. So Roger Penrose.
Well, thank you very much for that introduction. It's a great pleasure for me to be here. As you can see from the title here, I'm trying to argue that we need some new physics to understand the mind. But in what sort of way? I think we need the new physics anyway. So it's not just any old new physics. It's something rather particular which I want to talk about. Anyway, I guess I have to stand here now because of the moving the slides along. Now you see the question, I have a list of things at the beginning about various people's idea about what it is that creates consciousness, and it's quite a common view with computers getting so powerful now that it's just an issue of computation in some sense, some kind of computation or some complication or some power or something or other. That's not my view. You might say it's not computation, but maybe it's physics. Physics we know, and that's adequate to understand how consciousness comes about. That's still not my view. My view is that we need physics beyond the physics we already have. However, I want to make clear that it's not number 4, which is that somehow it's something quite independent of physics. So I do argue that physics is important. We need something new in the physics. It's something that we need anyway, which is new in the physics. Not just for consciousness. I'll come to that shortly, and I hope I can manage to get this thing work. I won't say much about psychology and biology and all that stuff. In fact, I won't say much about most of the things people talk about when they talk about consciousness. They talk about the feeling of pain or the feeling of love or the perception of the color green or all sorts of things like that. I'm going to concentrate on one particular issue. Sometimes people talk about all the different things consciousness is important for, and that's interesting and significant, certainly true. And I think one has to understand all those things. but I'm only concentrating on one particular thing, which is the quality of understanding. And I only do this because I have something to contribute. I believe I have something to contribute in that area, whereas many of the other things I really don't know what to say about them. So it's not that I'm saying it's particularly important, or think it is rather important, but the quality of understanding is what I want to try and address most specifically. And in the middle of this picture, I guess I can use the pointer, can I? Yes, here we go. I want to relate consciousness to intelligence, and I can't even read my own writing, and my eyesight is very bad, so I'm afraid I won't be able to read my own slides very likely. I want to say that that understanding is something which is necessary ingredient to intelligence. I would say it's not appropriate to talk about a device as being intelligent if it doesn't have the quality of understanding, at least our usual usage of these words. Likewise, I wouldn't think it's appropriate to talk of a device that it understands something without actually being aware of it. So although one may not understand in any deep way what any of these words mean, the connections between them I think are important, and that understanding is a quality which involves awareness, and that if you're considering a device which you might consider to be intelligent, then I consider that the quality of understanding needs to be part of its activities. Okay, so let's move on. And I have to move on this way, don't I? Now you see, this is an example I made up a few years ago. There was a series of chess positions made up by David Norwood and William Hartston, and there was a whole, I think there were about 100 different positions, and it was a sort of Turing test. You had to try and tell could you tell from their responses which, there were two groups of individuals looking at these problems. One were human beings and the other were computers, and could you tell from their responses which were the computers and which were the humans? And it was very clear, because the computers were very good at solving problems that were just very, very complicated with no particular idea behind them, and the human beings were good the other way around. If it was a simple, relatively simple position, but there was an idea that was clearly expressed, then that's where the humans would shine. And it was that distinction which impressed me. And one in particular of their problems had a row of pawns going right across the board from one side to the other, and the computer had no idea that that somehow separated one side from the other. And this was a little bit based on that, but it's a position which I made up to try and see whether computers could do what's the right thing to do. Anybody who really knows much about chess will realize it's a completely drawn game, even though the black pieces, there are more of them. One point I should mention is that you see there are 3 black bishops, but they're all on the same color. And that is a position you might think doesn't come about in an ordinary game. It could, because you have to make sure the position's a legal position. It is legal because there are enough black pawns to queen at the back of the queens, but instead of making queens, they make bishops. So that is a legal position. You have to check that carefully to see it's a legal position. It's a legal position, but you see that up in the left-hand corner, most of the black pieces are, and they're all trapped. Whatever they do, they can walk around a little bit, but they can't get out. And also there's a free bishop running around. It can't do too much because all the pieces, apart from the king, are necessarily on black squares, and so that being on a white square, the bishop can't do anything. So it's clearly a draw. Okay, you give this position to Fritz, and Fritz tuned at sort of grandmaster level, and it loses. Now I was rather expecting it would lose. I wasn't totally sure it would. And what happens is, if you keep it's useful to keep your white king somewhere down in the bottom left corner, and what happens is after a while it gets, well, you see, how does the computer judge who's winning? And if you ask it, it thinks black is winning. It always thinks black is winning. Thinks is the wrong word to use, I should say, but I use that just to make the sentence easy to say. It considers, perhaps is better, considers that the black is winning. Simply it does some kind of a count on the positions, and it judges because there are 2 extra bishops, 3 extra bishops altogether, and an extra knight, and so that should clearly be an advantage to it. And it presumably plays lots of moves. black, white, all sorts of different combinations, so I imagine it does that, and it doesn't make much impression on that, so it considers that it's a drawn game. No, sorry, I said that wrong. It considers it's a win for black, whereas you can see it's not, but it considers it's a win for black. So it comes to the point where the 30 move rule comes in, and that says if no piece has been taken, no pawn has moved, then it automatically becomes a draw. And so the machine considers that it's a draw if it simply doesn't have a piece taken or a pawn moved, and you can't move any of the pawns. So therefore what it does is it moves the bishop up next to the king and sacrifices it, which is a completely stupid thing to do, but nevertheless that's what it does, because otherwise the game is a draw. And since its judgment is that it's a win for black, a draw is therefore a disaster. So it has to sacrifice the bishop. Then, of course, the white king has can clean off the couple of pawns there and let its two pawns and make two queens. You really have to make two queens, I think, to get through the barrier. And the king itself has to march itself right up to the top here and creep in through the back, and you sacrifice one of the queens and then the other one checkmates. It takes a long time, but nevertheless, you don't need to be a grandmaster to see that you can win this position after the free bishop there has sacrificed itself. Anyway, this is just an example to show the difference between understanding something about the game of chess and simply computation. That's the point it's trying to illustrate. Even though the computation is at a much greater depth than a human being would do, the mere fact that you can understand something significant about the position trumps the fact that you simply compute many steps ahead. The machine does that. So that was just an example. I did have an example also with the game of Go, which I won't show you. It's not an example, it's an idea more than an example. And I rather hope that a competition will be set up. There is a move to do this. Competition was set up by AlphaGo or Alpha Plus against, say, a good Japanese player or somebody, and that the human would win under the circumstances. I don't know whether that would be the case. It would be very interesting to see. I won't say any more about that because I don't want to give too much away about it. But for the moment, let's constrain ourselves to the game of chess, or even Go if you like. The point about these things is that they are finite games. They're finite, so at some point, simply brute computation will eventually win. And where it's interesting to see the difference is with the infinite. Now, I guess I'm going to do it from here. Now, you see, sometimes people who aren't mathematicians think, infinite? Well, how can you really think about the infinite? You can. There are lots of things you can do thinking about the infinite. It's not so hard. For example, if you add two even numbers together, you always get an even number. If you add an even number and odd number, you always get an odd number. Those are statements simply about the entirety of natural numbers. Natural number, I mean 0, 1, 2, 3, 4 whole numbers which are not negative. And you can make quite simple statements about natural numbers which are completely clear, true or false, and nevertheless you're talking about the infinite. So people who say, well, the infinite is something you simply can't think about, that's not true. The infinite sometimes you can quite easily think about. Okay, now let me move ahead here. I should keep one hand. Here I have a sort of cartoon to represent a Turing machine. A Turing machine basically is the basic idea upon which modern computers are based. And this is a sort of cartoon illustrating it. The Turing machine itself, TM, is the little thing in the middle, which is the device here. And you see it's relatively small. It has a relatively small number of different steps and operations that it can perform. But nevertheless, there's the potentially infinite, or let's say an indefinitely large storage space. So I've had these little trucks which move backwards and forwards, and they've got these tapes all stored in there. And every now and again you have to feed the tape backwards and forwards, and that's the sort of idea that Turing had originally. Of course, it's nothing like the electronic machines we have now, but it's the same sort of concept. You have a relatively small finite object which does all the computations, and everything else is in the storage. So if you have a program, of course the program can be quite complicated, but you put that in the storage. So that could be potentially as large as you like, but the actual computation carried out by a very finite device. Okay, so you can talk about the infinite with finite devices, and the most, oh, I have to do it this way again. The most familiar way of doing this is what one learns at school, which is called mathematical induction. Suppose you have a statement which depends upon a natural number, and I say natural number, I mean 0, 1, 2, 3, 4, a whole number which is not negative. And you want to show that a certain statement which depends upon any natural number n, is that true for every number n? And what you do in ordinary mathematical induction is to establish first of all that it's true for the number 0, and that could be one finite thing to see. And the second thing is that if it's true for a particular n, then it's true for n plus 1. So those two can be little finite operations. First of all, that it's true for 0, and secondly, the statement that if it's true for n, then it's true for n plus 1. And there are many things you can see, nice simple formula that one learns at school, which can be proved in this way. So this is a way of establishing, by a completely computational total procedure, whether a statement which depends on all integers n is in fact true for all n. In fact, it's a technical thing I've got at the bottom, which is called first order piano arithmetic, which means you have ordinary logical things, you know, ands and ors and for there exists and things like that, logical statements, together with the principle of induction. Okay, now I want to give you, oh, here we go. This is a famous theorem. You see, in the introduction it was mentioned that I went to lectures that was nothing to do with what I was actually supposed to be doing at Cambridge when I was a graduate student. One of them was a course on mathematical logic by a man called Steen, and I've been sort of intrigued about the idea of Gödel's theorem. I'd never seen it before. I'd heard about it, and it seemed to say that there were things in mathematics that you couldn't prove. And I didn't really like that idea very much. And when I went to Steen's lectures, I learnt a bit more about what it really said. He taught us about the Turing machines, and so I learned about what computation really means. And when you use the word computation, you really mean the action of a Turing machine. Of course, it doesn't have to be one like the cartoon I showed you there. It can be much more sophisticated, but the electronic devices we have are basically have the same sort of structure. So that is a Turing machine. And so I'm talking about computations. Now, the Gödel theorem I'm going to phrase in a way which is really Turing's version. So this is Turing's version of Gödel's theorem. And what it says is if you have a system of rules R, I'm calling them R, these are things, basically a computer program. You could put these rules on a computer, and they have to have the property. You see, you have the rules R built in, and then you say, here's a mathematical statement. Can you prove it using the rules R? And the machine chugs away and chugs away and chugs away, and maybe it comes up with the end and it says, yes, we've used those rules, and yes, it's true. Now suppose you have rules like that you trust. This is the important point. The point is that these rules aren't just nonsense rules. They have to be rules that if you see what they are, then you believe that following those rules actually does give you a proof. And the proof means that you actually have to accept it's true. So you look at these rules R very carefully, you say, okay, the first one, is that all right? Yeah, that's okay. How about number 2? I'm not so, yeah, okay, I see that. And you go through all the rules, and you see that if you follow them correctly and the answer comes out, yes, it's true, then you believe, yes, it's true. See, proof isn't much use if it gives you something, and just following the rules, is that any good? Well, you have to know that those rules actually only give you true statements. Now, the very amazing thing about the Gödel statement, I found it absolutely stunning, is that what you produce is a statement which I call G of R. G of R is a mathematical statement of the same nature as the kinds of things that R is geared to decide for you. This statement G of R has the property, and you look at how it's constructed, and you see it has the property that it's definitely true as a statement if you trust the rules R. So if you really trust the rules are, that is to say, that if the rules are say, yes, it's true, then it is true, then G of R is a true statement. And you can see that clearly from the way it's constructed. Nevertheless, G of R cannot be proved using the rules R. Now, when I learnt that, I was stunned. I was blown, whatever the right word is there. And I thought this is really amazing, because what it tells you is that your understanding, that I'm using the word understanding here, your understanding that the rules R only give you truths transcends the rules R themselves. So that is, G is more or less using your understanding that these rules are correct, they don't give you falsehoods. Knowing that, you can, having that trust in R tells you something is true beyond the scope of R. So it's a clear distinction that what you gain from understanding what the rules are saying and what you get from following the rules are is quite different. And that blew me away, the fact that that's the case. And again, as it was mentioned in the introduction, I went to lectures that weren't supposed to be anything to do with my subject. Another course was a course given by Herman Bondi. That was not Hoyle, but I did know Hoyle. I went to talks he gave too. But this was a course given by Herman Bondi, and it was a very beautiful course on Einstein's general theory of relativity. So I had formed a good understanding of that theory, in a good part from those lectures given by Bondi. And also there was the lecture course given by Dirac, as we heard. And thinking about the course on logic and the fact that one seemed to have this quality of understanding, which didn't seem to be the application of specific algorithm. When I say an algorithm now, I mean following things like the rules are here. It didn't seem to be something like an algorithm, but understanding seemed to be beyond that, and something which seemed to require one's consciousness in order to appreciate it. But being a physicalist, in the sense that I believe that the world operates is according to the laws of physics, I had to think, well, what in the laws of physics can be something which goes beyond some kind of algorithmic procedure? Now, there is a point here which one has to think about, namely that when you do computation, you're talking about discrete operations. And when you do physics, you often... Sorry? Oh. Oh, I see. Chalk talk means I can answer a question. Fine, go ahead. Yes.
I'm trying to understand this completely. So there are two things that I have a question about. One is where you say you can construct a mathematical statement. So my first question is, if you say that, isn't that process of constructing that mathematical statement itself a proof for that statement? And secondly, following that, you say, if we believe in the validity of R, we must accept as true. Isn't that kind of the definition of a proof? Like, we accept it as true because it follows from some, axioms or something?
I don't know. Perhaps I missed I've forgotten your first question. What was that again?
The first question is, you say we can construct a mathematical statement. So
doesn't mean it's true, though. Now I construct this following is a mathematical statement. If you add two odd numbers together, you get another odd number. That's a mathematical statement which I've just constructed and it's blatantly false. So I'm not
how do
sure.
you know it's true?
How do I know it's true? I know it's false. I
You have an example, a counterexample.
If you read Gödel's proof, you'll get the answer to your question. Because he actually constructs the question in that proof. So that's the way to answer your question. It's actually a long, detailed answer.
Yeah, you have to look at it in detail. I mean, roughly speaking, what it does, if you follow the meaning, you see, the key point here is it's not just the symbols, it's what they mean. In fact, there's a theorem, which I could have referred to, I think it's called the Löwenheim-Skolem theorem, which says, you see, what you could do here, you consider your logical system R, and you could say, let's have a stronger one. And the stronger one is you include G of R as well. Now, that is stronger than R itself. And then you can prove G of R because you just put it in. But on the other hand, you might have said, let's put in G of R as false. Now that's just as consistent as putting in G of R as true. So just the logical operations don't tell you whether you should accept G as being true or G as being false. And you can be just as consistent adding G is true as including G is false. However, the first one, because you have to know what the thing means. And you have to know it's talking about natural numbers, or is it talking about some funny mathematical things which are quite different. And you can have systems like that. But if you're really talking about the natural numbers, then you know it's got to be G of R is true. And that you get from your understanding. And as just been described, the way G of R is constructed, it more or less says, I am not provable by these rules. But you have to see that you can formulate that within the rules, and being able to do that, you see that it's got to be true. If I've said it the right way around. Yes, it says I am not provable by the rules. I hope that's the right way around. Because if it is provable by the rules, then it has to be true. If it's not, I'm sorry, you have to think about it the way right. Is it that I am provable by the rules, or that I'm not provable by the rules? I'm not provable by the rules, I think is what it says. Anyway, from the logic you can see that it has to be true, but you have to know that the rules, following the rules, also gives you only truths. And then you've got to look at the rules. It depends on what they are, specifically. But they have to be things that you accept are correct rules of procedure. They're correct, they give you truths out of truths. And you look at them carefully and make sure you agree with that. So you need to do something like that, otherwise what's the point of the rules are anyway? You can say, okay, you have any old rules and it says yes, it's true, or no, it's false, and you have no reason to trust them anyway. So they've got to be rules that you really have reason to believe in. I mean, they could be quite subtle reasons to believe in, but they've got to be of that nature, otherwise they're not giving you proofs. So that's the whole point. And then what the Gödel thing says, that if you've got a system of such statements which are manifestly true when you examine them, then you must see that G of R is also manifestly true, but not derivable by the rules. I don't know if that answers your question.
So it would take this is something that would take a whole semester to understand. So, but let's accept it.
It doesn't take a semester; it takes 2 lectures. So. No, Steve was very clear on this.
Say I am unprovable.
Is it provable?
Yes, I'm not provable. Yes, that's right. Yes.
Yeah, I'm not questioning the validity of the whole statement. I'm just trying to understand how you're constructing your argument for what you're about to
So
say.
read Gödel's proof. It's very interesting.
Yes.
Gödel creates just kind of what he said there. But it's not a simple proof. So go ahead and read that, and your mind will be blown too.
Yeah,
There's an excellent
if I have to give that
page
lecture
that walks through a version of the proof itself. And it's very elegant. And you read through it, and you prove to yourself each of the statements that are made. And at the end, there's a straw man argument that sets up that's inconsistent and is a proof of Gödel's theorem. So
Yeah.
I would check Wikipedia for that proof.
Yeah, but the details of it, yes, it's hard work. Now, Steen did go through this in his course, and so it was convincing to me that the argument was correct. If it hadn't been, he shouldn't be giving a lecture at Cambridge, but you can't use that as part of the proof. No, but the conclusion I came to was that if we just operate according to some algorithm like this, then how do we know that G of R is true? So there's something in our understanding which goes beyond computation. Now there are all sorts of questions here. One of them, maybe there's an algorithm we don't understand in our heads, of course, and things like that. Let's come to that. But the first point that worried me is that the laws of physics, as we normally consider them, depend on continuous parameters. We talk about Newtonian mechanics, or general relativity, or things like that. They all depend on differential equations and things like that. They depend on the infinite. Well, you can usually get away with approximations, and there is a question about, are these approximations good enough? It's a question. Now you see, I'm not saying that I resolved that issue. I came to the conclusion myself, for some reason which I've probably forgotten, that it's not just a question of that. It's not just a question. You can have things like chaotic systems which depend very critically on the input, originally, and so you might worry about how accurately you can get your simulations to approximate the truth, and is there something deep in the fact that you're only using discreteness as opposed to continuum? It's a question which I'm leaving open here. I don't think that's the answer. What I do think is the answer is something quite different. Namely, that, well, I worried about things I learned about, Newtonian mechanics, which I learned about in my undergraduate course. I learned about general relativity from Hermann Bondi, and we know now from the LIGO observations. How do they know that this little blip of a complicated signal is two black holes spiraling into each other? Well, because a vast amount of understanding how to put GR on computers and carrying out these operations with computers. I sort of witnessed this thing proceeding decade by decade until they got up to the point where you really could simulate what happens with two black holes spiraling into each other. And it's very crucial that one had those calculations in order to know that the signals that are picked up by LIGO really are very good evidence that these really are black holes falling into each other, or something of that nature. So this illustrates, I didn't know at the time, how well GR can be addressed by computational procedures, but it was clearly something you could put on computers. So it seems to me it's not a question of space-time being curved and general relativity. What about Dirac's lecture? Well, we just heard about Dirac's lecture. Wonderful course of lectures. I thought I really learned a lot from them, and I thought they were brilliant. Lots of people told me, oh no, they're just the same as his book. They were, but I hadn't read his book at that time, so it doesn't stop them being brilliant. Anyway, this was... but the first lecture I went to, there was this question of a piece of chalk and all that. The point was that you have this principle of superposition in quantum mechanics, which tells you that if one thing can happen, or if another thing can happen, then you have all sorts of things which involve this and this at the same time. Schrödinger sort of took this to an extreme by talking about, well, I should say that the, I'll come back to this later, but the point was that you seem to have this thing which didn't follow the equation. You see, you have the Schrödinger equation, which tells you how a quantum state evolves in time and its differential equations. And again, put that on a computer can be quite difficult for various reasons. You need a very large number of parameters. But nevertheless, it is still a computational thing. So if our brains are in some way acting non-computationally, where can it be? Not in GR, not in quantum mechanics, as following the Schrödinger equation. But the thing that Dirac was mentioning in his first lecture was the other aspect of quantum mechanics, which has to do with, you can have superpositions, yes, here and here at the same time, but when you measure something, suddenly you see one or the other. And what's going on with a measurement? There's something very strange there, and it's not following the Schrödinger equation, and so it seemed to me, I mean, you could say it's a weak argument, it's the Sherlock Holmes argument about the dog barking in the night or something. If you try all the explanations that you can think of, then whatever is left must be the truth. It's that sort of an argument, which Oki would say is not an altogether the strongest argument you'd like. Nevertheless, it's a pretty good argument logically, and if one can't see anywhere else where the following of differential equations is describing what the world is doing, well, the other place is in the reduction of the state, or with a piece of chalk in two places, you look at it and it becomes one or the other, or something like that. Or you measure it and it becomes one or the other. Of course, some people thought it was the looking at it by a conscious being makes it one or the other. I'll come back to these things a bit later. That's not my view. My view is that it physically does one or the other, and the process by which it does that is necessarily part of our brain actions which do something which is not computable. So it's a kind of rather long-winded and tenuous argument in many respects, but that was the point of view I had. Let me give you some examples. I want to say something about another thing that the Gödel theorem applies, and basically Turing's looking at it, I think, gave you this kind of thing, is that there are certain well-defined problems in mathematics for which there is no algorithmic solution. There is no computation which will say whether it's true or false. And this is illustrating an example of that. This example is whether polyominoes, and when I say polyomino, what do I mean? I mean a shape in the plane which consists of a finite number of equal-sized squares stuck together along the edges. So that's what a polyomino is, and I have some examples of polyominoes, a little cross at the top and a little table-shaped thing there. And the property that I'm interested in is whether you, if you have a set of these polyominoes, a finite set, can you cover the plane without gaps or overlaps? And I have examples at the top of a single shape. The cross does it. You can see that just by continuing indefinitely the small region I have there. In each case, it does in fact tile the whole plane. How about the example at the bottom? Well, you can take either the left-hand one, and you see it doesn't work. You always run into a little gap somewhere, and it just takes you not long to convince yourself that it doesn't work. What about the right-hand one? Again, you always find there's a little gap somewhere. It doesn't work. But if you have both together, then you can see the arrangement underneath it. That does, in fact, you can see there, this continues indefinitely by repeating it. And here we have a single shape, which is a little bit more complicated to see how it repeats, but nevertheless it will do. And those are examples which will tile the whole plane. Now, how about the following example? There are three shapes now, and they do tile the whole plane. Here you have a finite example of those three shapes tiling the plane. It's not so easy. If you sort of look at it, you may not see any pattern about how it repeats, for good reason, because the only way that you can tile the entire plane with those three shapes is a way, following what I've got you up there, which never repeats itself. Now this is an important example because there was a theorem, well, there was an attempt by a Chinese-American mathematician Hao Wang. He was dealing with not actually quite this problem, but it was related, very closely related problem. It was for square shapes, single squares, but where you had edges that were coloured and you had to match the colours. And the question was, if you had these squares with matching the colours, can you tile the whole plane with them or not? And Hao Wang came to the conclusion that yes, there is an algorithm which will tell you whether or not these will tile the entire plane, if it's true that given such finite set of these shapes, that if they will tile a plane, they will do it in a periodic way. So they will do it in a way which keeps repeating itself in both directions. If that's the true case, then there is an algorithm. But then a student of his I've gone and forgotten his name just in a moment. A student of his showed that it was actually not true that there was an algorithm. There is no algorithm for the tiling problem with these one tiles, as they're called. He was able to show, as a sort of consequence, or one way around or the other, I forget which, that there is a large set of these little coloured squares which will only tile the plane in a non-periodic way. I think he had several thousand of them initially. He got it down to a little bit over 100, I think. And then another mathematician, Raphael Robinson, managed to get it down to 6 different tile shapes. But the one I've given you here is based on something due to Robert Ammann. I can come to this perhaps in a minute. I guess to move this forward I have to do this, don't I? Here we go. Now this is another example I made up more recently. I should say that if you want the algorithm for tiling the plane for... Oh no, I'm going to go backwards. I've lost it. How do I go backwards? 2 back, is it? That's it. But if you want to know how to tile the plane with those 3 shapes, there is an algorithm, and that algorithm is to look through my collected works until you find the right paper, and it tells you how to do it. But the real algorithm is basically due to Robert Ammann, and this was a development of some shapes he produced. They weren't polyominoes, but this was to make them into polyominoes. Okay, so let me go on from there, and I've got to do it here. Well, yes, what I wanted to say is that if you tried to do it, yeah, it would be an interesting problem. Suppose you gave those 3 shapes to a computer appropriately programmed, just try everything. How far would it get? It would be intriguing to know how long or how much computation it would take to get something as big as that. If with shapes the size that you've got here, could you tile the whole floor of this room? Well, you can, because you can do any big size you like. But if you just ask your computer, well, take one shape, try the other one, see which will fit, make it as big as you can, make it as big as you can, go back if it doesn't work, put in another shape. If that doesn't work, go back, try a different one, and so on. It's a very time-consuming or computation-consuming algorithm. It's really more than exponential, and it very rapidly becomes beyond the capabilities of I would say, any computer yet built. I don't know quite how big you'd have to have a region for that. I would guess, I'm just speaking off the top of my head, that probably tiling the floor of this room would be beyond the capabilities of such a computer. It would be interesting to see whether that's the case or not. Okay. Now let me give you another example.
Wait, how did you do that one? Did you do it by hand?
I drew it by hand, yes. Is that what you mean?
Yeah, I mean,
Yeah.
so
I did it
you
by
had
hand.
an algorithm in your head which allowed you to...
Yeah, no, I did it by hand, yeah.
Right.
But I mean, I can tell you something about the algorithm. No, you have to do it sort of top down. There is a procedure which tells you that you've got to build certain shapes out of those tiles or you get stuck. And if you build those shapes, they are sort of larger versions of the original shapes. And so if you know what you would do if you want to tile this room, you do it with about 4 tiles to begin with. Then each one of those you subdivide into smaller ones, subdivide, and then you get the answer. So it's done that way.
So you could still program a computer to implement the algorithms
Yes.
in your head, right?
Yeah. No, it's an algorithm, sure. No, definitely you could do that. But the problem is not that particular tiling set of tiles will or will not tile the plane. The thing that's not computable is the general problem of will a set of polyominoes tile the plane or not. And that's not computable. So there is no general algorithm which always works for any set. The particular one that I can give you for that set works for that set. But there will be other sets for which it doesn't work. And there is no algorithm which works for any such set. And that's a theorem. This is another example which might be nice to put on a computer too. Here we have just 3 shapes. They're just a square, a regular hexagon, a regular dodecagon with lines marked on them. You can't very well see the colours. There has to be one on the other side to the stripes, so you have to match them the right way around. That's done by how far up the edge they are as well, so you don't actually need the colours. But the question is, could you do that? And I suspect it would take a computer a long time to cover the whole floor without getting it wrong. Let me move on to show you what the sort of thing looks like. Here you have a nice example. Those are just the lines. I haven't drawn in the hexagons and the dodecagons and so on. But you see you have patterns like that which keep changing. It never quite repeats. It sort of almost repeats. This big thing over here, for instance, seems to be repeating itself down there. But if you look at the things next to it, they're different. And so it has to be, never repeats itself. And you get, I should say that this picture was made by a computer, but it was made by a computer according to the algorithm, which I could tell you if necessary. That one is not on my collected work, so you have harder time finding how to do it. I have a tiling which it's based on, which is in my work somewhere, but I think it's the same article. But this particular thing I just showed you is not explicitly anywhere, except in a talk I gave somewhere. Now let me continue. I just wanted to illustrate, those examples are illustrations of how understanding something can certainly achieve something which computation is hard to achieve by. So it's sort of illustrating this business about what people call deep learning, I think, where you have a computer which simply runs through, it has no understanding itself, it just runs through vast numbers of possibilities, far more than the human being can do, and maybe uses some kind of pattern recognition principles which again run through vast numbers. Does it really understand anything? That's the question I raise, you see. It's doing something which looks a bit like understanding up to a point, but it's different. And I'm claiming that understanding is different. Now, here's this example which was proved by Goodstein in, I think, 1945, does it say? And it's a very nice example of something interesting which I'll come to. You can explain to people who don't know much mathematics. All you need to know is A, how to write numbers in a binary form, and more generally other bases. Let's take an example. I'm taking the example of 1077. And the first thing, you've got a couple of operations you apply to the number, and I'll describe what they are. The first one is to write that thing in binary, which I've just done. What does that mean? Well, it means you write the number as a sum of powers of 2, of distinct powers of 2. And the 1s are where the power of 2 is in there, and the 0s are where the power of 2 is not there. And every natural number can be written in such a way. That's well known, but I'm not anywhere near finished. The second thing is to look at the exponents there. Those exponents involve other numbers than 2, so you might say, well, we should write those exponents also in terms of binary, or in other words, sums of distinct powers of 2. Well, I've done that. The 8 or something is 2 cubed. You'd have to look at it. My eyesight's not very good. Okay. Then you say, well, I still haven't finished because I've got a 2 cubed or something up there, and that needs to be written in such a way as well. So we have to keep going until we run out. You may have to go to exponents of exponents of exponents up to a certain level, but it'll come to an end somewhere. Okay, now I want to describe the two operations. I've got the number written in terms of powers of 2, or the exponents are powers of 2, and the exponents of the exponents, and so on. It's always powers of 2. Now, two operations. One is replace all the 2's by 3's. So I now have a ternary representation instead of a binary representation. Okay, numbers got a lot bigger. That's operation A. Operation B is subtract 1. Okay, so it's gone up enormously, and then it's come down. I can't see whether I've done it. Has it come down yet? Okay, now we take all the 3's. Somebody better tell me, my eyesight is so bad I can't see the greens very well. The 3's, the
It's
greens
all
are
threes. It's all 3's all the way down.
all the way down.
You haven't subtracted 1.
And now I have to subtract 1, so let's subtract 1. And, okay. Now I make all the 3's into 4's, and then I subtract 1. It's not so easy now because I think it's like subtracting 1 from 1,000. You've got to have 999, so it means I have to put coefficients as well, so those are the 3's and so on. But they're always smaller than the base, so that's all right. Then all those 4's go to 5's, and then I subtract 1, and then the 5's goes to 6's and subtract 1, and the numbers get bigger and bigger and bigger and bigger. And what does 1077 get? Well, it gets to, you can see the roughly the numbers are as indicated there. They get bigger and bigger and bigger and bigger until you reach 0. Now that's a hare and the tortoise. The beads, all hares and the tortoises, more or less. The hare is the increasing the numbers, and they get huger and huger and huger. But the little subtracting one, picking off the one by time, finally wins. And that's Goodstein's theorem. And you can prove this using a certain procedure. Before I get to that, let me tell you what you can't prove it by, and that is you can't prove it by ordinary induction. And this was a theorem due to Paris and Kirby. They showed that the Goodstein theorem, which tells you it always goes to 0, cannot be proved by the mathematical induction, which I showed you before. So the algorithm, the first order piano arithmetic or something, that algorithmic system does not prove Goodstein's theorem.
And you know it goes to 0 because if you subtract 1,077 times, it's going to be 0. So you know how many steps you have to go.
Ah, yes, but see, you don't just do it that many times. It's much, much more than that. Because it's written as the powers, and then those numbers go big, and those numbers go big too. So it's much, much bigger than that. It's absolutely huge. In fact, to illustrate that, let me just give you the way you prove it, and this is only of any use to anybody who knows about this. The way you, I'm so sorry. No, I get lost with these things. The black splotches, you just cover up the base numbers by a splodge, which stands for the first ordinal number, first infinite ordinal number, omega. And this is an example of what's called transfinite induction. So there is a procedure which tells you it's true, but it's not ordinary induction. It's a sort of Gödel procedure. You have to go beyond it, do something beyond that. Okay. Now, it's a nice example not just as something that you cannot prove by ordinary induction, but as something which is beyond the capabilities of current computers anyway. See, I have the number 1,000 and whatever it is, 77. How about starting with a small number? How about 3? Well, you can go home and work it out for 3. It comes down after a few steps, not hard. How about 4? Okay, I recommend that you do not try and put it on your laptop somewhere. You don't put it on the mainframe. You would not put it on any computer existing today to try and follow through directly to see how 4 comes down to 0. I would recommend take a good piece of paper and a pencil and try and figure it out yourself. And with a bit of persuading, you can probably see that 4 will eventually come down. But it's not something that you do. You don't actually do it. You just see that it works. So you use your understanding that 4 will eventually come down. Okay, to do the higher thing is a little more complicated than that, but it's kind of intriguing that even with the number 4, you have something which you could see is true, but if you blatantly put it on a computer without thinking about it more than that, exactly what you're doing and why a certain number of steps are going to do such and such and such and such, without that kind of understanding thought, it's not going to work. So these are just examples to show you why understanding, there's something subtle about it, which is not simply carrying out an algorithm. Now you see, you might argue, as people often do, that algorithm in our heads, still believing it's an algorithm, is so complicated and difficult, and it's beyond our direct understanding of it. So you can't use the Gödel thing to give you something that's true, because you don't know what that algorithm is. Now, I did address these things in my book, Shadows of the Mind particularly, but I don't want to do that here, because there's a much more direct argument, which I give you in the following cartoon, which is given here. You see, here I have a picture, a cartoon which I drew, which is supposed to represent our ancestors trying to do various things, such as in the distance you see they're growing crops, they're domesticating animals, they're building shelters, they're doing all sorts of things that they are using their understanding for. Slightly on the right-hand side you see that they have cleverly built a mammoth trap, which the poor old mammoth has collapsed into. And so again, they use their understanding to promote their well-being. In the foreground, we have a poor mathematician here who is fiddling away with a nice piece of... And there's a little bit of a joke about that theorem. I won't tell you the joke. But he is actually trying to prove something here. And he's a good mathematician, but he's about to be devoured by the saber-toothed tiger. And the argument here is that being a mathematician is not really a selective advantage. which I think is probably true, but the point I'm trying to make is not that. The point I'm trying to make is the general quality of understanding, yes, that definitely is a selective advantage. It's interesting to think, what about that, you see, the Gödel theorem in a way? I mean, what's that got to do with it? Well, you see, what it's got to do with it is that you really have to understand what the thing's about. That's the key point. It's not just that you follow the rules, you understand what the things mean. And it's always necessary to know what they mean. Because as I said from this Sloan-Goldman thing, that you can put the Gödel thing in, or the negation of the Gödel thing in, they're both just as consistent. But one of them is doing what you want, it's what you mean, and the other one isn't. And this question of knowing what things mean and so on, that's where your conscious understanding is really coming in. Now, it's very hard to know what it actually involves, and to quantify that in any real sense is a genuine problem. And I agree with that. All you can see basically here is what it's not. And what it's not is following algorithms. It's understanding what algorithms are. And the Gödel thing is a little bit like that. You've got your algorithm, how do you defeat it? How do you get around? How do you do something better than the algorithm? Well, you know what the algorithm is, you understand it, you understand what it does, what it's based on, and that enables you to go beyond it. And I'm sure that sort of thing is very much involved in coding and what people do in all sorts of secret organizations and goodness knows what. Anyway, that's my example. I should say that this is also, it's meant to be...
By the way, does the saber-toothed tiger have understanding of what...
I would think so, yeah. You can see, I like to think of let me come to the next slide. This was, I like to think that the mathematician has some understanding too, but it wasn't doing mathematics that was the selective advantage. It was the general way which understanding can relate to other things in the world, and that's the amazing thing. Let me try and go on with this. Okay, well, you see, this raises this question. What I'm trying to argue is that mathematical understanding is not a computational thing. But that's a very, very narrow thing. People often say that. And why do you concentrate on this teeny little narrow? Well, that's because I can say something about it. That's the it's not. I'm not trying to say it's more important than other things like the consciousness of the feeling of pain or whatever thing, or love, or other qualities which involve consciousness. Sure, it's just that those are the things I can say something about. I can't say much about the sensation of the color red, for instance. It's a conscious perception, but what do you do with it? I have no idea. Whereas these mathematical things, you can go ahead of that. So I want to say, okay, it's not just mathematical understanding. What about human understanding? Well, that's part of it. What about human consciousness? Well, what about animal consciousness? And then we come to the saber-toothed tiger, if you like, all various things which I'm often impressed by, often in these David Attenborough programs. Sometimes I can't remember which ones were on the David Attenborough program, but one I remember seeing was a program where you saw these African hunting dogs. And they were going along, and then they came to a sort of fork in the road, like a path or something. And half of them went one way and half of them went the other way. And why were they doing that? Well, you see, the other half go and they find a herd of antelopes, and they start growling and yelping and whatever they do, and they chase them away, and they came right to the place where they have to cross the river. And the place where they cross the river is a narrow place, and just as they get to it, the other lot pounce on them. And they make a great mess of the poor old antelopes. But you see, there's something understanding there of what those hunting dogs. I mean, they haven't been using deep learning to say, well, we try going this way, that way, and they do that a million times. They have some concept of what they're actually doing, which may well involve some concepts of what they think the antelopes think. I think it's something like that is going on. So there's some perception of the kind of feelings that the antelopes might have. Okay, we'll scare them. You know what that means they do? And okay, so it's something like that. There are other examples which I get impressed by. One of them is octopuses. And you see, you could say hunting dogs aren't so far from us in evolution, but octopus is completely different. And one example which I really liked was there was a little tank with the octopus in there, the poor old octopus in there, and this octopus was supposed to pull a chain and open the door and gave it some food. And this octopus was doing this, and it got pretty well fed up with the whole thing. And it just yanked the cord off and rose itself to the top and just started squirting the various people with white coats all around. I'm hoping, I don't know whether this was true, I'm hoping that the people with white coats said, God, there's an intelligent being there, we better let it out and put it back into the sea. I'm hoping they did that. I'm not at all sure they did. But it did indicate that there's something, okay, the octopus just got fed up. And what does that mean? What's the selective advantage of getting fed up? Well, there may be one, that it wasn't at least in the tank, because it removed its little door opening the food for it. Another example I like too was something about elephants. And there was this herd of elephants. I don't know if herd is the right word for elephants, but never mind. And it's always a female who's in charge of the elephants. And they'd gone one place, and they had to go a long, long way to go back where they needed to go. And instead of going straight back, they made a big detour at one point to the place where the sister of this leading elephant had died. And her bones were in this place. And the whole herd went there, picked up the bones, and started passing them around from one elephant and caressing the bones and so on. I mean, what's that got to do with selective advantage? I have no idea. But it's got something to do with a feeling that the elephant evidently had, that there was some conscious presence that was now removed by the death of her sister, and that somehow she could reenact that in some way by going to the place where she died. I mean, it's something clearly beyond directly advantageous effect that one might see in having conscious feelings. Okay, well, let's move on from there. Okay. What about, I say new physics? What new physics? And this comes back to the Dirac chalk. Now here I have a picture that I was invited to give a talk by the Hans Christian Andersen Society in Odense in Denmark, and I thought, why on earth have I been asked by the people to celebrate the 200th anniversary or something of Hans Christian Andersen? And then I thought, well, I did write this book, The Emperor's New Mind, whose title was a play on the Emperor's New Clothes, the Hans Christian Andersen story. So I thought, well, I suppose that's why I've been invited. And I thought I'd better think of another Hans Christian Andersen story to illustrate what I was really interested in at the time, namely the foundations of quantum mechanics. And at one point I gave this talk. At one point, I think at the end of the story, the poor mermaid is in a bad way and she's lying there. And the story is that when the sun comes up, it's in the night, and when the sun comes up, the first ray of light hits the mermaid and she dies. So what I thought is, well, we'll put a beam splitter in between that first photon, half-silvered mirror, and so the photon is split into one which kills the poor young mermaid, and the other one goes off somewhere else. So she's Schrodinger's mermaid. She's dead and alive at the same time. So I used that in the story. But this picture was not to illustrate that. This picture is to illustrate something else. It's to illustrate quantum mechanics, or really the two things we do in quantum mechanics. The bottom part of the picture, if you go back to the original picture, is under the sea, and you see sort of all entanglements with these growths, and you see the fish and various things like that, and the seaweed is all tangling them up and everything like that. So you have this entangled world of quantum mechanics underneath, and the top world is the world of sort of discrete things, and we seem to understand better, of the classical world. And so that's what it is. It's illustrating these two ways we look at physics. At the quantum level, we use Schrodinger's equation, or what's called unitary evolution, a clear-cut differential equation which evolves the state in a deterministic way. And at the top, we have the classical world, which we seem to have to use when we're talking about bigger things, in some sense. Now, what's the mermaid doing? Well, she represents this mysterious thing that Dirac, I suppose, was allegedly supposed to have explained with his piece of chalk, although I suppose he said something which just to calm us down in some way. Namely, what the mermaid is doing, she's partly under the water and partly above it, and she represents the measurement process, if you like, or the reduction of the state. So I like to use the word U for the unitary evolution, that's what goes underneath the sea, C for the classical evolution, that's what goes on above, and R for the reduction of the state or the collapse of the wave function, this mysterious thing which seems to connect the two worlds. And that is the big mystery of quantum mechanics, is how is it? It's just simply following the Schrödinger equation does not give you, well, you see Schrödinger himself when he described his poor cat was talking about something, theoretical example of what happens when you follow his own equation. What you get is a dead cat and a cat which is both dead and alive at the same time, and he was more or less saying this is nonsense. The real world does not behave like that. We're missing something. We're missing something deep and important. And that is the point which I sort of got from Dirac's first lecture in a sense. I didn't know at the time that not just Einstein, who was worrying about the foundations of quantum mechanics, Schrödinger from this example, clearly also, de Broglie, who worried about similar things, but Dirac himself. You have to find the right quote. But Dirac, you can see if you find the right quote, believed that the quantum mechanics that he was influential or instrumental in formulating is an incomplete or a provisional theory, I think he said, that we need to go beyond current quantum mechanics to get a consistent picture of the world as a whole, which incorporates whatever is really going on in this collapse of the wave function. So that is a thing which, ever since Dirac's talk, I've worried and worried and worried about. Now, the point I'm going to try and make here is the route that I've taken to a possible resolution of this big problem. I should say that there are many people who do try to go beyond standard quantum mechanics. Let me get a bit of water here. We do try to go beyond standard quantum mechanics and introduce strange new fields or ideas or something or other. I prefer to go from a different point of view. I want to consider the two basic 20th century theories. One is Einstein's general relativity and the other is quantum mechanics, and to try and see how they relate to one another. Now here we have the basic principle underlying Einstein's general relativity, the principle of equivalence, basically Galileo's experiment, or thought experiment probably, of dropping a big rock and a little rock from the Leaning Tower of Pisa, and he was well aware that atmosphere would make a difference and you had to worry about the friction in the air and so on. But if you could idealize it so that you could ignore the atmospheric effect, then the two rocks would fall together. Another way of saying it is if you have a little insect perched on one of the rocks, there's a little insect looking at the other one, and as far as it's concerned, during the fall, there doesn't seem to be any gravity. So you kill off the gravity simply by falling freely. And here we have a sort of futuristic Arthur C. Clarke sort of space station, and the space astronaut who doesn't notice the gravitational field of the Earth simply because he's falling freely in the Earth's field. It happens to be not downwards but around it, which is rather handy, but nevertheless it's falling freely. It's the same thing. So that's the principle of equivalence, which is the foundation stone of Einstein's general relativity, and the other is the principle of superposition, which I described in terms of a piece of chalk or whatever. Now, here I have a very condensed form of the argument, which I had some various arguments, but with this one is the most compelling, I think. What I want to do is consider an experiment on the tabletop. So here we're doing a quantum experiment on the tabletop, and I'm going to suppose that in that experiment, there are people really working out the theory behind this experiment, and in that theory, how do they incorporate the Earth's gravitational field, which we assume is a uniform field downwards? Well, what most physicists would do would simply be incorporate a term into the Hamiltonian, and you just proceed as though gravity was like anything else, and who cares? And that's a way of doing it. Now you might say, but perhaps Einstein was sitting in the corner and watching what you were doing, and so you get worried. Oh no, we shouldn't do it that way. We'll do it Einstein's way. I should say the little letters, I think, are the Newtonian way, if you like. That's the Newtonian perspective, where you just put another term in the Hamiltonian. You treat the gravitational field as just another force, or a potential term which you put into the Schrödinger equation. And the Einsteinian way is, no, you don't do it that way. You consider there is no gravitational field, but you've got to use coordinates which freely fall. So they're freely falling, and the capital letters, I think, are the freely falling ones. And there's a simple relation between one and the other. And what you get? You don't put the free gravitational field in now, but you just took the freely falling coordinates. What you find is almost exactly the same thing both ways. That is to say, that you have the capital psi, which is the Einsteinian one, and the Newtonian one, which is the green one, I think, which is the little psi. And the only difference is that there's this phase factor. So this is a number which is just a complex number of unit modulus, and the usual procedures of quantum mechanics, if you work out probabilities, you simply take the squared modulus of each side, and since you've only got a phase factor between the two, who cares, you say? Well, you can use one or you can use the other. That's not actually quite fair. It's not quite fair because you have to look carefully at this term which connects the two wave functions, and that term involves t, that's the time, cubed. You might say, who cares? Okay, it's still just a phase. But if you're really doing your quantum theory right, or more correctly, if you're doing your quantum field theory correctly, you need to know what the vacuum is you're talking about. And what that really means is you need to know how to split your field amplitudes into positive and negative energies. You have to know what positive energy is. and that means positive and negative frequencies. And this means normally you split your thing up into Fourier components, you look which one's positive energy, and you keep those ones. Trouble here is with the T cubed, it messes all that up. And it says you're in a different vacuum. So strictly speaking, the Newtonian way and the Einsteinian way are different quantum field theory vacuums. Again, you might say, who cares? You just stick to one vacuum and you get the right answer. Okay, that's fine. What I'm going to do now is slightly to change the problem. Slightly. But changing it in a way which is crucially different. As part of the experiment on the tabletop, I'm considering that there is a lump of material, and at a certain point in this thing, it is put into a superposition of two locations at the same time. So this lump of material, this is one instance of it, and that's the other instance here, and these two are in superposition. Now the problem here is that if you imagine a little insect sitting here somewhere, and that insect is trying to consider how to use this formula I have above it, and the trouble is that as the point moves around, you get a different superposition, and you're in trouble, because there is no way, according to standard quantum field theory, how to proceed in accordance with the Einsteinian perspective, which says your gravitational force is really an acceleration, because you're superposing states in two different vacua. This is the sort of G's that I've got here, and I think this is battery is fading out, isn't it? I'm afraid. So you've still got probably. Oh, can you still see it? If I keep it on, it seems to disappear. You've got a superposition of two different states, two different vacua. That's cheating in quantum field theory. So you've got to cheat. I don't know of any way of doing it which doesn't involve a cheat. So what I do is to involve the cheat and to take into account the cheat. That is to say, I know I'm cheating, and I say that this cheat is a certain error in my calculation. And then I integrate the cheat over the whole of space, and I say that is a measure of the error I'm committing in doing this cheat. Then you find, by doing an integration by parts and various little tricks, you see that that cheat, which I'm calling EG, this uncertainty in the energy, or because I haven't done it quite right, it causes an uncertainty in the energy, is, well, I can actually reinterpret it in the following way. I consider my object here, which I think when I point at it I have to be careful not to do it too long, it vanishes. The object here has a certain mass distribution. When it's here, it has a different mass distribution. So what it amounts to, and this is just mathematics, it amounts to the following. Take the mass distribution here, subtract from it the other mass distribution. It's just a trick. I take this mass distribution, subtract the other from it, and I work out what's called the gravitational self-energy of that difference. That's a well-defined calculation in the Newtonian limit. I do that calculation, and that is the EG. So the EG, another way of saying it, if this is simply a translational displacement, is if you imagine that there were two lumps sitting there, originally on top of each other, and I gradually pull them apart, how much energy would that cost me if I only consider the gravitational traction? No other forces whatsoever, they don't come into it. Just the gravitational traction of the lump in one instance with the lump in the other instance, and how much energy would it cost me to pull them apart. And that's another way of getting the EG. Okay, now what I say is that that EG is a fundamental uncertainty in the measure of the energy of the system as a whole. And then I use the sort of Heisenberg time energy uncertainty principle in reverse from what people normally say. Normally it's if you have an atom which is a certain decay time, then the reciprocal of that decay time is an uncertainty in the energy of the atom. Now I'm going the other way around here. I'm saying this system has inbuilt a certain energy uncertainty, and therefore that system has a lifetime. And that lifetime, I claim, is for it to go from the superposition to one or the other. And that is the formula which Stuart Hameroff and I try to incorporate. I have to find this point here. There's another way of saying it, which is rather nice. Think of it in space-time terms. So if we have the history of that lump, so at the top of the picture, I have the history going up to the upwards and to the right, and you think of the space-time of having a little kink in it due to the mass of the lump. Now, as I move the lump into a superposition of two locations, then the space-time becomes a superposition of two slightly different space-times. But as soon as that difference becomes what's called a Planck unit in volume, Planck unit, this is the sort of fundamental unit when you try to combine quantum mechanics and general relativity together, and you find that it's a sort of basic uncertainty in the nature of space-time. What this is telling you, that when that splitting of the two space-times becomes of the order unity in these units, then it goes to one or the other. So that is the contention. That's what we call OR. OR stands for two things, of course. Well, OR stands for objective reduction. So it's the reduction of the state or the collapse of the wave function, and it's objective. So it's not somebody looking at it. It actually does it itself, irrespective of conscious beings around or not. It's simply a physical process. It does one or the other, and the lifetime is given by this formula. So that's OR, and it's OR deliberately because it says or. It says one or the other. It's not the superposition of the two. It becomes one or the other. But this moment at which the splitting takes place, according to the hypothesis that Stuart Hameroff and I tried to develop, is what we call a moment of proto-consciousness. So it's a physical thing. It doesn't have to have living beings around it. It's happening all the time. It's happening in the atmosphere all the time. But it's almost always completely random and has no purpose to it. It's just nothing. It's proto-consciousness. We don't say it's consciousness, but the argument is that consciousness is the building block out of which consciousness is constructed. So that is the point of view we adopt. I think I've only got 2 slides, or maybe 1, of relevance here. This is a curious feature. Many people have theories in which you get superpositions, and you might imagine that here, this is time proceeding up to the right diagonally, and except I can't make the light go on. Here we go. And the idea is that it becomes one or the other after a certain criterion is satisfied. Some people worry about this because they have theories which do that, but it jumps from a superposed state to a single state, and this involves some sort of energy in their theories, and this is a real problem because systems sort of heat spontaneously, and this is a feature of almost all these theories. But the proposal I'm making is rather exotic in this respect. It's what I call a Stalinist view. It's a rather unfortunate word, perhaps. Sorry, you probably showed me how many minus seconds I've got, but what I'm trying to say is that it's as though, when the choice is made up here, it was really as though it was made well earlier. In fact, as though this thing never existed. So you see these photographs of somebody in the Politburo who had disgraced himself in the eyes of Stalin. And he's there in the photograph, so they had to rub him out from the earlier pictures. So it's the same sort of philosophy here. I don't like the, perhaps I should remove the name from the picture, but nevertheless, it's that kind of idea that although you have to go up to here before the criterion becomes felt, it says that the choice was made much earlier. That has a role to play in some of these consciousness experiments. I'm not quite sure how much we take that seriously. That is more or less the end, except for 2 things: experiments. This was a long-term experiment, been going on for about at least 15 years, maybe more, by Dirk Barmeister. This is a cartoon of his experiment. This experiment doesn't look much like this now, but the idea is that you have at the top left a beam, you have a laser, a half-silvered mirror, a beam splitter. The photon goes 2 ways at the same time. One branch of the photon's existence you keep in a cavity up at the top right. The bottom one comes and is kept in a rather funny cavity which you reflect it backwards and forwards between a hemispherical mirror and this little cube thing here, which I've magnified up. And you imagine that this thing is now put into a superposition of being moved and not moved, depending upon whether the photon came this way or the other way. And if it's big enough, and if you can keep it there for long enough, bashing it about 1,000,000 times with a photon, then it becomes one or the other, maybe. And then you retrace everything back, let it go back, and see whether you retain coherence with the initial thing. Now, it's quite possible that within 2 or 3 years from now, an experiment will demonstrate this. This is a cartoon. It doesn't look much like that. But Dirk Barmeister, when I visited him in Leiden in the Netherlands about 8 years ago, he spontaneously, without prompting, said, in 10 years we'll have an answer. I thought, well, maybe, you know, experimentalists, that's probably a constant in nature, 10 years. But the next time I saw him was 2 years later, and he said in 7 or 8 years we'll have an answer. So I thought, ooh, that's important. Then I saw him again in Marseille, and he gave a talk, and this was about 8 years after my previous, this was just a few months ago. And he said in about 2 or 3 years we'll have an answer. So I thought that's pretty good. So maybe we'll have an answer. There are also experiments using Bose-Einstein condensates which have not yet been put into play by Yvette Fuentes most particularly, and she has ideas about putting these very quantum mechanical things into superpositions of two states and whether they will reduce to one or the other in the time scale that the theory says. It would be fascinating to see if this is true. This is important not just for consciousness, but even more importantly probably for physics as a whole. But what about consciousness? Oh, here's something which let's not bother about. This is when the energy is a little different. Let's not worry too much. But how does it apply to consciousness? I had no idea. I wrote my book, The Emperor's of New Mind, trying to learn about neurophysiology, and I couldn't see anywhere where this thing could come in. Nerve propagation seemed to be much too disturbing of the environment. And then Stuart Hameroff, who had read my book, wrote back to me and he said, I gather you don't know about microtubules, basically. And I thought this is much more promising. So that's the sort of picture which he's put forward, and this is the sort of overall picture. You have to have lots and lots of these microtubules, and the idea is that there will be some kind of quantum coherence in the microtubules, which when you have many of them acting all in some kind of concert together, then they will reduce the state in a meaningful way which relate to consciousness. It's a huge step. Well, it's a big step already to seeing whether the physics behaves in the way I'm proposing it might. It's a much bigger step to see how this thing will relate, if it does, to the way the conscious brain actually works. And it will be fascinating to know how all this goes. Thank you very much.
We hope you have enjoyed this video.